Section 2.8, the derivative as a function. We use, in this section, we use f prime of x for the derivative of f of x. This is just a notation, f prime of x. So the way you say it, this is f prime of x. So f prime of x is equal to the limit we defined in the previous section of f of x plus h minus f of x over h as h goes to 0. That was the main definition of the derivative. So if we need to find or apply this to specific examples, so find f prime of x if f of x equals x cubed plus x minus 1. To do so, we just apply this definition, the limit as h goes to 0 of f of x plus h cubed plus x plus h minus 1 minus f of x all over h. Limit as h goes to 0. This is x cubed plus 3x squared h plus 3xh squared plus h cubed. That's the formula. I'm using the formula a plus b all cubed, which we reviewed back during the first week in the packet, the journey to calculus. Keep the x plus h the same, minus 1. Multiply the negative sign in all over h. These cancel. The 1 minus 1 cancel. Negative x cancels. We can factor h on the top. 3x squared plus 3xh plus h squared plus 1 all over h. The h cancel, and when we pass the limit, that gives us 3x squared plus 1. 3x squared plus 1. We may look at a different example now. Find the derivative for the function f of x equals negative x all over x plus 1. Negative x over all x plus 1. F prime of x, again, it's the limit as h goes to 0 of f of x plus h. So we replace every x with x plus h minus negative x over, so the function itself all over h. Then how we're going to simplify this? The first step is on the top we get negative x minus h all over x plus h plus 1 plus x over x plus 1 over h. The best thing to do here is to find the least common denominator, all of them, which is x plus 1 times x plus h plus 1. So we multiply this by x plus 1 times x plus h plus 1. We do the same thing for the next fraction, x plus 1, x plus h plus 1. Same thing for the denominator. Now the things simplify out. These cancel. Negative x minus h times x plus 1. This cancel. X times x plus h plus 1. H times x plus 1 times x plus h plus 1. Now we always keep this denominator the same, and then the numerator we multiply it out. Negative x squared minus x minus hx minus h plus x squared plus xh plus x. So I distributed everything. negative x squared cancel, negative x cancel, xh cancel. So now the only thing left is h, which simplifies with this. There's a negative 1 left, x plus 1, x plus h plus 1. Pass the limit as h goes to 0. So this is negative 1 over x plus 1 square. Another example. So what are we going to do with this one? Find the derivative for this function, f prime of x equals limit as h goes to 0. F of x plus h means we're going to replace every x with x plus h minus the function itself all over h. Now we multiply by the LCD, which is 2 square root of x plus h square root of x. 2 multiply the second fraction by 2 square root of x plus h square root of x. And we do the same thing in the denominator. 2 square root of x plus h square root of x. This cancels. Square root of x minus square root of x plus h. If we happen to pass the limit, that will give us 0 over 0. So what do we need to do here? We need to rationalize the numerator. So we multiply by the conjugate of the top one plus limit as h goes to 0. On the top you get the square root of the first one square minus the second one square. Keep the denominator the same. On top we get x minus h. And then for the next one, what do we get? These cancel out, the h cancels out. If you pass the limit as h goes to 0, you get negative 1 over 2 square root of x square root of x times square root of x plus square root of x. That gives us negative 1 over 2x, 2 square root of x, which is negative 1 over 4x square root of x. That's the derivative of that function. Now we introduce a definition. We say a function f is differentiable at x equals a if f prime at a exists. If f prime at a exists, it is differentiable. So we say it is differentiable over the interval ab, or the interval negative infinity to infinity, or a to infinity, or negative infinity to a, if it is differentiable at every point in that interval. net f of x equals the absolute value of x. Is f differentiable? Well, what is f of x absolute equals absolute value of x? This can be rewritten as plus x if x is positive, or negative x if x is negative. So we're going to do, we have two different functions. We start with f of x equals x. So we're going to find the derivative of this one using the main definition, h goes to 0, of f of x plus h, so it's x plus h, minus the function over h. Notice these cancel out, and that gives me the limit as h goes to 0 of simply h over h, which is the limit as h goes to 0 of 1, and that gives me 1. And we do the same thing for the other one, f of x equals negative x. F prime of x equals the limit as h goes to 0 of f of x plus h. So we replace x with x plus h minus the function itself all over h. This equals the limit as h goes to 0, negative x minus h plus x all over h. These cancel out. Limit as h goes to 0 of negative h over h. That's a negative 1. Notice these two functions, or these two derivatives, are not the same. 1 and negative 1 are not the same. So when we found the derivative for x and for negative x, they are not the same. So we say the function f of x equals absolute value of x is not differentiable. It's not differentiable. Graphically it means if we graph it, it goes this way, this way. This part of it is the plus x, this part is the negative x. So the function is not differentiable at x equals 0. Not differentiable at x equals 0. Notice here, not differentiable. Notice as a note, no tangent lines can be constructed at x equals 0. So if we have a function like this, we can't draw a tangent line here. No tangent line or lines can be drawn. Same thing if it's this way. No tangent lines at those sharp points. Another case is where the function is not differentiable when there is a vertical tangent line like this at point A. So this is a vertical line. So why it's not differentiable here? Because the slope is undefined. Slope is undefined. So not differentiable at point A. And this point A is called cusp. Another case when you have a function that goes this way, or let's fix it. Say we have a vertical tangent line like this. So you can have this function, same thing, at this point here, it's not differentiable. At this point, because of the vertical tangent line. So also, as a note, we can say a function fails to be differentiable at corner points. we call them cusps, at sharp points, as we saw in the absolute value of x, at vertical tangents. Or vertical tangent lines, and at the point of discontinuity. So if you have a function like this, see at this point the function is not differentiable because it's discontinuous at that point. Important theorem to introduce here. The theorem said if a function is differentiable, then it is continuous. Automatically it is continuous. Note that the converse is not true. So if it's continuous, doesn't mean it's differentiable. And one example on that is the absolute value of x, the one I showed you earlier. Even the cubic root of x. These functions are continuous functions, but not differentiable. Not differentiable. So now we got some notations here to introduce. We got some notations. First notation, f prime of x, is we can use y prime for that. We call the first derivative of f of x. Or y prime can be written as dy dx, or d of y with respect to x, or some people write d sub x means the derivative of the function with respect to x, or d of f of x with respect to x, or the d of f of x. They all mean the derivative of the function. All mean derivative of the function. And based on that, we can introduce what we call them higher derivatives. Higher derivatives. In higher derivatives, what we have, if y prime is the first derivative, we can find the second derivative, which is the derivative of the first derivative. So if you take the first derivative, find its derivative, you get the second derivative. So that's called the second derivative, which can be written as the derivative of the first derivative with respect to x, or d squared y dx squared. That's the notation for the second derivative. For the third derivative, it's the derivative of the second. So that's called third derivative. Notation wise is d cubed y dx cubed. Fourth derivative. This can go on and on until the nth derivative. Nth derivative. So if we look at an example on this, let f of x, this is the function that we started with today. And what we did, we found its first derivative, f prime of x, which is 3x squared plus 1. To find the second derivative, we find the limit as h goes to 0 of not f of x plus h. It's for f prime of x plus h minus f prime of x all over h. And how do we finish that up? well, we look at the f prime, the function. We replace every x with x plus h, square plus 1, minus the derivative itself, all over h. Now we try to simplify. On the top, we get 3x squared, 2xh by 3, 6xh, plus 3h squared, plus 1 minus 3x squared minus 1, all over h. This cancels this, and the 1 cancels. We can factor an h out, 6x plus 3h, all over h. The h cancel each other, and that gives us 6x. That's y double prime. We can do the same thing for y triple prime. So y triple prime is the limit as h goes to 0 of f double prime of x plus h minus f double prime of x, which is this one. This is f double prime of x, all over h. So for this one, we replace x with x plus h, minus 6x over h. Here we have 6x plus 6h minus 6x all over h. These cancel out, and the h cancel out, so all we get is just simply 6. Now we are going to find y to the 4th derivative. So this is the 3rd derivative here. Again, limit as h goes to 0 of the 3rd derivative of x plus h minus the 3rd derivative of x, all over h. For f triple prime of x plus h, we need to replace every x with x plus h, but we don't have any x's, so it's just 6. And the same thing here, over h. So remember, h is not 0, but it's approaching 0. So here we get 0 over h is going to be 0, and that's a 0. So from there on, any derivative we find is going to be 0 from there on. Some applications to derivatives, where do we apply them? We introduce s of t to represent the position function at time t. That's what this represents. V of t is the velocity function at time t. A of t is the acceleration function at time t. What's the relation between them? V prime of t, if I find V of t is the derivative of s of t, or we can say ds dt. The acceleration is the derivative of the velocity, or that can be written like this, or the second derivative of s. So it's d squared s dt squared. So that's the relation between position and acceleration and velocity. And to see an example, let s of t be 2t squared minus 5t. Find the acceleration. So v of t, we first need to find v of t, then we find the acceleration from there. V of t is defined as prime of t, which is the limit as h goes to 0 of s of t plus h minus s of t all over h equals the limit as h goes to 0, 2 times t plus h squared minus 5 times t plus h minus the whole function all over h. Let's simplify this one before we pass the limit. 2t squared 4th 2h squared minus 5t minus 5h minus 2t squared plus 5t all over h. These cancel each other. The 5t cancel. On the top, I can factor an h out. 4t plus 2h minus 5 over h. These cancel out. And that would give us 4t minus 5. So this is only the velocity, but we need to find the acceleration. Now the acceleration is the derivative of the velocity. So it's the limit as h goes to 0 of v of t plus h minus v of t all over h. That gives us the limit as h goes to 0. This is v of t. So replace every t with t plus h minus 5 minus the whole function v of t all over h. Limit as h goes to 0. 4t plus 4h minus 5 minus 4t plus 5 over h. These cancel, and then equals the limit as h goes to 0 of 4h over h. These cancel, so the answer is 4. Now, one last thing to talk about here, how f and f prime are related graphically. I have a chart here that I came up with. This is the graph of the function, that's its derivative. So if the graph of the function goes this way, it either has a minimum point or a maximum point like that, then the graph of it at that point will go on the x-axis. It will become on the x-axis. That's the first one. If it's going up, like increasing the graph of f, then the graph of its derivative would fall above the x-axis. Above the x-axis. If the graph is decreasing, if it's decreasing, the graph falls below the x-axis. Below the x-axis. So if we have a graph of a function and we are required to graph its derivative, so let's say it goes up this way, down, and then up. So this is f. This is the graph of f. This is O. We need to graph its derivative. Okay, so notice something first. This is increasing up to point A. It's increasing. So the graph must fall above the x-axis. Something like this. And then it's decreasing from here, from point A all the way down to here to point B. It's decreasing, so it should fall below the x-axis. Okay, it should fall below the x-axis, and then it's increasing, so it should fall above the x-axis. So this is the graph of the derivative. Keep in mind that's just a sketch, not like perfect. Your graph might look a little bit different if you try it, but it's fine. This is okay. So if you follow these guidelines in the chart, you will be able to graph any derivative for any given graph for a function.